Hello and welcome to this lightning talk on buffer overflows. My name is Daniel, I am the Vice President of MonSec and the creator of majority of the binary challenges in this CTF, and majority of the challenges, or the binary challenge in this CTF, are buffer overflow challenges. That is because it is by far the easiest type of memory corruption. So, before we jump into to actually exploiting a buffer overflow, you kind of need to know a little bit of the theory behind it first. Buffer overflows, by definition, are a form of memory corruption. So, what is memory? If you actually ask any of the lecturers at Monash, or you just Google it, you'll find that memory, or RAM, is basically just where all the data that the computer is using at any given time is stored. So, what does it actually look like? Well, it looks like this. This is the layout of memory. You've got your stack, you've got your heap, you've got your data and your text, and rah 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 rah. For today, you don't need any of that. All you need to know is this. Actually, that's a lie. You don't even need to know this. You just need to know what the stack is. The stack is basically just a bunch of 32-bit long data chunks stacked on top of each other. If you've ever done Python, or if you're currently learning Python, think of a list. RAM is basically just a very large list of 32-bit values, and instead of an index, like 0, 1, 2, 3, they have little hexadecimal locations. So, that's all you need to know. Forget about the rest. So let's think of a simple C program. C is probably the lowest level programming language that you've probably encountered so far, and you probably will encounter unless you do, 1048, I think it is, that does MIPS, which is assembly, but getting off topic. This is a very simple program. Basically all it does is, it's actually only one function. It'll load some data into memory and then exit. That's it. So how does this actually look in memory? If we put a little breakpoint where this line is here, what will memory actually look like on the point after this has been loaded in and before it exits? Well, it'll look like this. This is what is called a stack frame. We only are looking at one stack frame here because the program is only made of one function. In a stack frame, you've got your local variables, you've got your buffer, you've got your other local variable, and then you've got something called a return address and an old frame pointer. You don't need to worry about this last one here. That's for more advanced things. But this, keep a note of this, we'll be coming back to it later. Alright. Cool, so this is where your three variables are, your local variable 1, your buffer, and your variable 2. You might be thinking that, okay, when it's in memory, it'll be like a bunch of zeros for the buffer, and then b, right? Well, I've actually got a program like it running here, and if we run it, we can see that not quite. The B's are actually up top, and the A's are down below. The reason for that is because the stack is a stack. Think of it like a stack of books. You initialize your variable here. You initialize this variable, and it gets put onto the stack. Then you initialize, you allocate 16 bytes to a buffer, and that gets put on the stack, and then the next one comes in and that gets put on top. So just be mindful that anything you do on the stack will be reversed to what the diagram will show. Or at least what this is showing. Okay. So what then? So what then was my point? Because I actually just forgot it. 1 second. Oh yes. So what then happens if we put something into the buffer? Well, let's put in my name. We'll type in Daniel, and as you can see, this is the hexadecimal representation of Daniel. This is actually what the buffer looks like at the moment, and it has been replaced on the stack. My name is now in the system stack. But a few of you keen-eyed ones will notice that doesn't look like that. 0x69 is not 0x44. What's going on here? Well, 0x44 does appear here. 61 appears here, 6e appears here, and 69 appears here. They are there. They're just reversed. But they're not reversed because they're still in order. But they are reversed. Confused yet? Yeah, don't worry, you'll join the rest of us. So, what is happening here? Well, it's something called Indianness. Back in like the 70s or 80s or whenever the first home computers were, there was a massive debate by computer scientists how data should be represented in memory. What kind of prevailed out of that is this really weird version, which you see today. But backtracking a little bit, the argument was between two versions. One called Big Indian, and one called Little Indian. Big Indian is probably what you expect, where the first byte goes in the first section, the second byte goes in the second section, and the third byte goes in the third, and so on and so forth. Little Indian kind of flips that, but only on the 32-bit chunk. So the first byte of the 32-bit chunk goes at the last part of the 32-bit chunk, and so on and so on and so on. Fun fact, this was actually named after the Indians in Gulliver's Travels, I believe. That doesn't matter, it's just something fun to know. Cool, so, alright. So the memory's in there, the computer knows how to deal with it. Wonderful, we've got our data in the buffer. So let's get to overflowing. What is an overflow? Well, as the name suggests, if 16 bytes have been allocated, what happens if we put in 17 bytes? Let's try it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Whew. We run it again. Let's get rid of this just for time's sake. And we see that we get an error. The array of characters is too long. The computer adjusted for this by just cutting it back down to 16 bytes. Unfortunately, it doesn't look like we can actually overflow the buffer. Sorry guys, I lied, pack up, go home. Not quite. Because what has happened is the compiler has seen this at compilation time, and it has fixed it for us. But what if we didn't do it hard-coded? What if we did this, but we did this at runtime? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. We put that in. We don't have an error. Well, ignore that, but we don't have that error, right? And as you can see, the full 17 bytes of the 41 or capital A has been input. And what has actually happened is because we were using a function called gets here, which is a very insecure function, it basically just kept going until we told it to stop. So it's actually overrun the buffer and has started to modify the section of the stack below the buffer. So it has actually started to affect this variable. As you can see, it's actually put the 41 in and the terminating character 00. The rest of the value has changed, but if we then call the variable b in this C program, we're not going to get the value we expect. We're going to get whatever the integer representation of this is, which it doesn't actually show me. Cool, so we can change variables. Wonderful. That would be really useful for changing things like bank account balances, credit debt, other financial related things, because hackers only want money. But that itself is cool, but we can only really change what's in the stack frame. We can't really change what's on the hard drive or anything, right? What if we did something a little more complex, and we actually controlled how the code flowed? So, if we go back to our stack frame cheat sheet, we can see that below the local variable was something called the return address. And the return address is what I alluded to as coming back to earlier. This is actually where the computer looks to know where to jump to once it's finished the current function. So what that means is that if we can modify the return address, we can jump to any piece of code we want. Okay, so where is the return address in here? Well, I can actually show you. If I put that in, I'll actually highlight it right here. The return address, in this instance, not always like this, is immediately below this variable. Makes sense. This is where the return address is initialized. The next variable initialized is the bunch of A's. Okay, so what happens then if we override the buffer with just a bunch of A's? We get something called a segmentation fault. A segmentation fault occurs because the computer's tried to jump to a location in memory that it can't access. And as we can see, the return address has been overwritten by 41414141, or the hexadecimal representation for AAAA. Cool. So if we were somehow able to find, say, the hexadecimal location of another function, we could just jump into that function, no worries. Yeah. That's pretty much it. That is the core concept of a buffer overflow, and that's really all you need to know to complete majority of these challenges. Before I go though, I will show you a few tips and tricks to make your life a little easier when trying to actually do this, because obviously this is a really easy program to exploit because it actually gives you the stack. The challenges won't do that for you. You won't be able to see the stack. Or will you? Because there is a nice little program called GDB, or GNU Debugger. Basically, on your Kali machines, or whatever Linux virtual machine you're running on, this will act as like a wrapper around whatever program you pass into it, and it will let you control and see what happens at each individual step. So, if we put in print stack, and we run it, we will get your name, input it, and we can see the program went as normal. But we can put in something like break main and run it again, and then it stops the program at the point where the main function begins, as you can see here. Sounds really cool. You can do things like next instruction, to see it step by step what's happening, and you can do it that way. If you use GDB vanilla, you're not going to look, it's not going to look exactly like this. That's because I have a plugin called Jeff, or GEF here. I highly recommend getting Jeff just because it makes things a hell of a lot more user-friendly. GDB is a very, very old program, and is very much the pinnacle of Linux, really. It's really, really powerful, but nobody actually truly knows how to use it. Unless you've got a plugin like this, where someone has figured out how to use it, and then gave it to you for free. So, the other thing that I want to show you is something called pwntools, or that. You can install it through Python or your package manager. I think it's just apt-get pwntools on Debian. But what pwntools gives you is a range of things that will allow you to modify and mess with buffer overflows and other memory corruptions. So, the one I want to actually show you is something called PwCyclic. So this will actually give you a string of unique characters in such a way that... well, actually, I'll just show you. So, if we put in PwCyclic 100, we copy this, we run the program... oh, hold on. We get rid of our breakpoint, we run the program, and we put that in. And if we scroll up to what the stack actually looks like, you can see that because of how this is constructed, how this string is constructed, each one of these data chunks is entirely unique. So what that means is you can take this, you can put it back into PwCyclic with the -l parameter, and it will give you a number. This number is actually the amount of padding you need. So if we just print a bunch of A's, this is the amount of padding you need in order to get up to messing with the return address without actually overriding the return address. So if I were to then concatenate, concatenate 11223344, we can see that I haven't actually counted for Indianness here, but the return address is what I have put in here. So that's really useful, especially when you're trying to control code flow into a very particular location. And if you want to use both of these tools together, you can copy that, run the program in GDB, and it will actually tell you, if you've got Jeff installed at least, it will tell you, otherwise it's just a little harder to find. It will tell you that the reason it crashed with the seg fault is because it tried to access this section of memory. And you'll notice if we plug it, if we plug this back into PwCyclic, this is how you get the padding. Yeah, hopefully that has helped. Hopefully you understand buffer overflows a little better. If you have any other questions, feel free to ask in the Discord, or message one of us directly, and we'll certainly try to help. Enjoy the CTF. Hopefully you guys can actually get some of these challenges before the end of the day, and have a great life.